in this video, we're going to finish up section 3.3, properties of functions, okay? And we're going to finish it up talking about something very similar to what we ended the last video on. And we ended the last video on local minima and maxima. In this video, we're going to talk about absolute maxima and minima, or minima and maxima. The order really doesn't matter, okay? So, the absolute minimum and maximum of a function is determined pretty similarly to the local minima and maxima definition, but there is something very important, okay? So it says the definitions are similar to the local ones, but now it applies to an interval in general, not an open interval, okay? So what I mean, great, fine. So now you need to look everywhere on the function, not just a small interval. So in general, the meaning of an absolute maxima or minimum, okay, is it's the smallest or largest everywhere, not locally. Okay, so in general, this should say maximum or minimum everywhere, not just locally. Okay? Sometimes absolute maxima and minima are called extreme values. Okay? So they may be called extreme values, and additionally, there may not be an absolute maxima or minima. Okay? So it might not exist. And so here's a theorem that sort of speaks to that point. If I have f, and it has to be a continuous function, whatever that means, we won't get to that in this class, whose domain is a closed interval a to b, okay, then f has an absolute maximum or minimum on that interval, okay, on that interval. So, an example or two about how that works. Okay, so let's actually go back to the your turn. So this is the your turn from the last video, hopefully that you've done. If we look here, we've got some local minima and maxima. Again, hopefully you've done this your turn. The local mins are here and here, and the local max is here. I want to find the absolute minimum or maximum and maximum of this function. Okay? And so the global minimum has to be the minimum everywhere. And so we have two options, -1, 1 or 3, 0. And it turns out that 3, 0 is the absolute min because it's lower than all points. Okay? This -1, 1, if I draw the open interval from here to here, then it's the lowest. Okay? But 3 is the lowest. 3, 0 is the lowest everywhere. Okay? So that's the absolute minimum. Is there an absolute maximum? Well, we see that this function is increasing seemingly to infinity on this side, and over here it's also seemingly to increase to infinity, so there is no absolute maximum. Okay? And so that gets back to the theorem I talked about. Okay? If I have a function that's defined on a closed interval, then we know it exists. But what this is an open interval, because this goes on this way until negative infinity, and it also goes on this way until positive infinity. So that's an open interval. Okay, so that theorem doesn't apply here, which means there's no absolute max. Now, on a contrary note, if, and just make believe here, that this function did not increase to infinity, and it stopped maybe here. Okay, so I'm going to put a point here and say that all of this above doesn't exist. Okay, and then I'm going to go over here and I'm going to get rid of that, okay, and then put another point down here, okay, and that's where this one stops. Again, getting rid of sort of all that, okay, just make believe that that is gone. Then I do have an absolute maximum because it's the most absolute point, the highest point everywhere, and since my function is only defined from about here to here on a closed interval, it turns out that this point that I drew up here would be the absolute maximum because it's the highest point out of everywhere on this function. Okay, so in this case, this would be the absolute max, and then this would still be the absolute minimum. So hopefully that makes sense. Okay, if it's an open interval, as in this thing just continues on forever, this way and this way, then there may not be an absolute minimum or maximum. But if it's on a closed interval like the one I just drew, then they do exist. Okay, so that is absolute maxima and minima. So here's another example. A few that will make you think a little bit and illustrate important points. If we look at example number 1 over here, okay, we have critical points. That critical points is an important term in other classes, but what I'm going to use it here as are the possible suspects for an absolute maxima or minima. And so for this one, it's the end, okay, the ends. It's defined on a closed interval from 0 to 5. The function doesn't goes from here to here, but nowhere else. Okay, and then I've got, maybe I can first call them local max and minima. Okay, right here, right here. I've got 4 points that are possible. And so first we'll start with the absolute minimum. By the extreme value theorem, I know that it exists. Okay, one exists because it's on a closed interval. Where's the smallest point out of all points on this graph? You might think, well, it looks like 4, 4 is a minimum, and you'd be correct. Okay, but the lowest point is 0, 1, down here. Okay, it's the lowest point, so it's the absolute minimum. Now I need to look for the highest point. I need to look for the highest point. And it turns out that it's what you think. It's 3, 6. 3, 6. Okay, because that's the highest point. I can't draw a line at 3, 6, but here. Okay, it's higher than every other point on that function. So what do we have down here? 4, 4 turns out to be a local minimum, okay, because I can draw some open interval maybe from here to here, and then that's the lowest point in there, and it turns out that 5, 5 is nothing. Okay, you might say, well, maybe it's a local maximum. But remember, for something to be a local max, it can't happen on the endpoints. It needs to happen in the interior. So I can't call that a local max. So hopefully that made sense. Now let's go over to number 2, which is a little bit more tricky. Okay, again, it's defined from 1 to 5. By the extreme value theorem, it says that either a local max or a local min will exist. Now the extreme value theorem doesn't say that both of them will exist, only that one will exist. So if I look here, okay, I've got 3 points that are possible suspects. 1, 2, 5, 3, and then maybe 3, 1. Now, 3, 1 is an open circle, and an open circle there means that it doesn't actually exist at that single point. Okay, so it exists. The function goes all the way up to the point on the left and the right side. Okay, but at that point nothing exists. And that's the part that's tricky here. So the clear one is an absolute maximum. Okay, hopefully it's clear that the absolute maximum happens at 5, 3. And so then the question is there an absolute minimum? Is there a point that is lower than all points on the graph? Your thought process should take you to say that yes, of course there is one. It's 3, 1. But again, that's an open circle there, which means it doesn't exist at that lowest point. And so the answer is there is no, or none, absolute, there's not none, there is no absolute minimum. Okay? So there's no point that's lower than every other point on that graph. Okay, I could look over here, close to it, but there's another point over here that's just as low. That 3, 1 would have been the lowest point if it was shaded in, but it's not. Okay, and then if we look, 1, 2 is on the endpoint, so it can't be local, so it's nothing for me. Okay, so hopefully that makes sense about absolute maxima and minima. Now the last thing that I would usually do in this section is talking about how to find those maxima and minima using the graphing calculator. But because we're in such a weird semester and I don't have access to that on my own, okay, and I can't very well show you on these recordings a graphing calculator, we're just going to have to skip this section for now until I come up with a better idea. Okay, so that's the end of this video. There are no your turns associated with absolute and minimum and maxima.